Good morning/afternoon, everyone. Welcome to today's presentation. I'm Associate Professor Yasser M. Madany. I'm a senior member of IEEE and a senior member of URSI. I'm excited to share with you our topic today, Z-transform and its applications in digital signal processing. Over the course of this presentation, we'll explore the fundamentals of the Z-transform, its key applications, and how it plays a vital role in digital signal processing. Let's get started. Let's start by looking at the introduction. Here, we set the stage for our discussion by exploring the fundamental concepts that underpin discrete time systems. Moving on, we'll delve into difference equations, which are essential for modeling these systems and understanding their behavior over time. Next, we'll examine how these systems can be represented visually through block diagrams, making complex relationships easier to grasp. After that, we'll explore the Z-transform, a powerful mathematical tool that simplifies analyzing and solving difference equations, especially for systems analysis. Finally, I'll give you an outline of what to expect in this presentation, so you can see how all these pieces fit together in understanding discrete time system analysis. This overview helps us stay focused on our main goal, mastering the tools and concepts needed to analyze and design these systems effectively. Let's take a moment to explore the concept of difference equations. These are mathematical tools that describe how a certain quantity changes from one step to the next. Instead of continuous change, like in differential equations, difference equations focus on discrete steps, which makes them very useful in modeling processes that evolve in stages or time intervals. The key idea here is that these equations relate a current value to previous values, allowing us to predict future behavior based on what we know now. This recursive nature is fundamental because it helps us understand systems that develop over time, such as populations, financial models, or even digital signals. As we go through this section, keep in mind that difference equations are a cornerstone in understanding how discrete systems operate, and they'll connect to many other topics we'll cover later in this presentation. So, grasping their structure and purpose is essential for the broader picture we're building. Let's take a closer look at the block diagram representation. This diagram is a crucial visual tool that helps us understand the overall system architecture. It simplifies complex processes by breaking them down into interconnected blocks, each representing a specific component or function. By doing this, we can see how data flows through the system and how different parts interact with each other. Highlighting these connections is key to grasping the system's operation as a whole. Connecting this back to our presentation theme, the block diagram provides a clear, high-level overview that makes the intricate details more accessible and easier to analyze. It's an essential step in designing, troubleshooting, and optimizing the entire system. Let's look at an example to see how our solution works in practice. This example will help us understand how the key concepts we've discussed are applied in real-world scenarios. By examining this, we can better grasp the effectiveness of our approach and how it connects to the overall goal of the presentation. It's a practical illustration that brings the theory to life, making the ideas more tangible and easier to relate to. Today, let's explore the concept of the Z-transform. The Z-transform is a powerful mathematical tool used primarily in signal processing and control systems. It helps us analyze discrete time signals and systems more easily by transforming complex sequences into a more manageable form. Think of it as a way to convert a complicated time-based problem into an algebraic one, making analysis and design much more straightforward. The key idea here is that the Z-transform takes a sequence of data points, like a series of measurements over time, and maps it into the complex Z-plane. This allows us to study the system's behavior in terms of poles and zeros, which are crucial for understanding stability and response. One of the most important aspects of the Z-transform is its connection to the Laplace transform used in continuous systems, but it's tailored for discrete systems. This makes it indispensable when working with digital signals or systems that rely on sampling. In the context of our overall discussion, understanding the Z-transform equips us with the tools to analyze and design digital filters, controllers, and other discrete systems. It bridges the gap between the time domain and the frequency domain, giving us a comprehensive view of system dynamics. Now, let's take a closer look at the properties of rock, or receiver operating characteristic, curves. First, one of the key points to understand is that rock curves are used to evaluate the performance of a binary classifier across different thresholds. This means they give us a comprehensive view of how well our model distinguishes between the two classes. Another important property is the area under the rock curve, often called AUC. The AUC provides a single scalar value that summarizes the overall ability of the model to separate positive from negative cases. A higher AUC indicates a better performing model, with 1 being perfect and 0.5 representing random guessing. It's also worth noting that rock curves are threshold independent, which means they consider all possible classification thresholds rather than focusing on a specific one. This makes them especially useful for comparing models or assessing performance without committing to a particular decision boundary. Finally, the shape of the rock curve itself can tell us a lot. A curve that bows closer to the top left corner indicates a strong model, while a curve closer to the diagonal suggests weaker performance. Understanding these properties helps us interpret rock curves more effectively and ultimately choose the best model for our specific application. So, for this slide, let's look at an example that highlights our solution in action. This example helps us see exactly how the concepts we've discussed come together in a real-world context. It demonstrates the practical application and effectiveness of our approach. By examining this example, we can better understand the key points and appreciate the value of the solution we're proposing. Remember, connecting these examples back to our overall theme is essential, as it reinforces how our solution addresses the core challenges we've identified. This concrete illustration makes the abstract ideas more tangible and easier to grasp. Let's continue exploring the solution. On this slide, I want to emphasize that these points are crucial to understanding how we can effectively address the challenges we've discussed so far. First, it's important to recognize that implementing these strategies requires a clear focus on key areas. For example, prioritizing innovation and adaptability can really make a difference. Second, we need to consider how these solutions connect to our overall goal of sustainable growth. By aligning our efforts with our broader vision, we ensure that each step we take is purposeful and impactful. And finally, I want to highlight that collaboration and continuous improvement are vital. As we move forward, staying open to feedback and refining our approach will help us stay on track and achieve the best outcomes. So, in essence, this slide ties together the practical actions we can take with the larger mission we're all working toward. Now, let's look at example 3, which illustrates an effective solution in action. Here, we see how applying the concepts we've discussed can lead to real, tangible results. This example highlights the importance of tailoring solutions to specific challenges, ensuring that the approach is both practical and impactful. Remember, the key takeaway is that a well-designed solution not only addresses the problem, but also aligns with our overall goals. It's about turning ideas into actionable steps that drive progress and success. Now, let's look at this example to see how the solution comes together. Here, we're focusing on a specific scenario that illustrates the key points we've discussed so far. Notice how the approach we take in this example highlights the core concepts and demonstrates their practical application. It's a good way to connect the dots and see how these ideas function in real situations. By analyzing this example, we can better understand how to apply these solutions effectively in our own work, reinforcing the overall theme of the presentation. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a look at this appendix, which is the Z-transform table. This table is a really useful reference tool because it summarizes the key Z-transform pairs that we've worked with throughout this presentation. It helps us quickly identify the transforms of common sequences without having to derive them each time. The most important point here is understanding how to use this table effectively. For example, If you see a particular sequence and you want to find its z-transform, you can simply look it up in this table instead of recalculating from scratch. This saves a lot of time and effort, especially when dealing with complex signals. Additionally, this table also shows the inverse z-transforms, which are just as crucial because they allow us to go back from the z-domain to the time domain. Connecting all of this back to our overall theme, the z-transform table serves as a foundational tool that simplifies the analysis of discrete time signals and systems. It's like having a quick reference guide that ties everything we've learned together, making the process more efficient and accessible. Thank you all for your attention today. If you have any questions or want to connect further, here is my contact information. You can reach me at my email addresses, Dr. Yasser, madany@yahoo.com or contact@imadany.com. Additionally, I'm available through my IEEE email at imadany@IEEE.org. For more resources or to stay updated on my work, please visit my website at https://imadany.com. Once again, I truly appreciate your time and interest. Thank you very much.